Okay, so good morning to all.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. Good morning. So we just start our session, today's session. So today's session is very simple. That is, it is related to the trees. Okay. So the different concepts related to the trees and how to generate the particular that is which type of the trees which are present inside the data structures, and then we just discuss uh, the details how to just uh, deal with binary tree and how to represent that particular tree and whatever the traverses related to the trees, and one more, that is how to convert the general tree or general tree into the binary tree. Okay, so these are the few concepts related to the trees. So let's start uh, the tree. Okay, so tree is one of the mostly used data structure which is very much useful for just storing the particular data in the hierarchical format. Okay, so whenever we are just considering the tree, then it is a set of one or more nodes where one node is designated as root and remaining node that are partition into non-empty sets, which are also called sets, each of which is a subtree of the root. Okay, so a tree is nothing but it is a combination of the particular subtrees which are connected with the root node by the edges. Okay, so whenever we just consider the tree, so this is the simple example related to the tree. So inside this particular example, when I consider this particular, so this is called as root node. Okay, so whatever the starting point of the particular tree is called as root node. Then these are the particular edges. So this is called as edges, edge. So edge is nothing but it will just connect two nodes. Okay, so here again inside the tree, suppose I'm just dealing with this particular structure. Okay, so this is one particular subtree. So this one called as subtree. Okay, so again T2 is a subtree. Again, whatever the DHI is again one more subtree. Okay, then here leaf node. Okay, so leaf node means what? The node which don't have any childrens. So this is called as leaf node. Okay, and these are the called as internal node. Internal node. That is, internal node means what? It is not root node, that is at the start, but it is not at the end also. So the internal nodes which have the connectivity between the particular nodes, so that's why it is called as internal. And leaf node means the nodes which are at the end, which don't have any particular children. Okay, so leaf nodes which don't have any child node. Okay, so this is called as leaf node. Then next that is the path. Okay, so path means what? Suppose I want to reach to the J. Okay, so I want to just reach to the J. So the path is from root node. Root node. Okay, so path started from root node to the J. So our path is A, C, G, and J. So this is called as path of the J. So whatever the nodes which are starting from the root node, it is called as the particular path. Then ancestor means what? Whatever the parent node. Okay, so ancestor means what? Ancestor means parent node. Parent nodes. For example, suppose I want to find the ancestor of this C. Okay, so ancestor of C is whatever A. Then ancestor of suppose I just say J is G, C, A. Okay, so these are the particular parent nodes which are available. Then descendant means what? Descendant node means what? The nodes which are the child of that particular node. Okay, so descendant descendant means whatever the child nodes. So for example, suppose I just take the example. So descendant of A is all this particular node. Descendant of B. B is E and F. Or suppose I just say G. G is J and K. So whatever the node which are child of that particular node, which is nothing but the descendant node. The next one, that is the level. Okay, so the level means what? The level number which is assigned to the particular level. So root level is at the 0 and whatever the numbers that can be just increased by the 1. Okay, so here let's see the level. Okay, so here level means what? Whatever the particular position of the elements or nodes inside the tree. So this is called as level 0. So levels are always started with the 0. Then this is the level 1. Then level 2. And last one, that is level 3. Okay, so whatever the levels, so 3 levels are there inside the particular tree. So this is called as level. Then degree. So degree means what? The suppose this is the particular structure. So for example, I just draw one more simple structure with the arrows. For example, B and C. So degree means what? The nodes which are coming to that particular node and which are outgoing to that particular node. Okay, so in degree and out degree. in degree and out degree. So in degree means what? The nodes are the edges coming to node. And out degree means what? The edges going from node. Okay, so what is the in degree of this particular A? In degree of A, that is the edges coming to node, is 0, but out degree is 2. Okay, because two edges are leaving for that particular node. That's why out degree is 2. Inside the B, for B, in degree is 1 and out degree is 0. Okay, so for B and C, these are the particular calculations. Okay, then here we have one more concept which is called as height of the tree. Okay, so height of the tree is nothing but whatever the number of uh, levels which are present inside the height of tree. So whatever the number of levels starting from root as 1 to last level. Okay, so for example, for this particular tree, the height is 1, 2, 3, 4. So height is 4. Okay, so these are the particular basic terminologies related to the particular tree. Okay, so whenever we consider the tree, then these are the particular basic terminologies related to the tree. So whenever I want to just deal with the tree, I have to just consider this much terminologies inside the tree, and then we can move forward related to the different concepts which are present inside the tree. Okay, so let's see one by one, moving forward with the different terminologies. Next one, that is which are the different types of the trees. So the tree having total 6 types. One is general tree, second one that is forest, third one that is binary tree, fourth one that is binary search tree, fifth one is expression tree, and sixth one that is tournament tree. Okay, so these are the particular total 6 types of the tree. So let's see one by one. So general tree are the data structures that stores elements hierarchically. Okay, so whatever the tree we just seen over here, so this is nothing but the general tree. So tree in which the particular nodes are organized in the hierarchy, and these are the connected with edges, and it is having the root node, then different edges, and they are having the leaf nodes, so are called as general tree. Okay, so whenever we just divide that particular tree, then it will just divide into the subtree. Okay, just so general tree which have 3 subtrees per node, are called as ternary tree. Okay. So general tree is nothing but whatever the tree. So whenever I just cut this particular root node, then it will just divide into the first part. Then this is the second part and this is the third part. Okay. So in this way, I can able to just, so this is my first part, this is my second part, and this is my third part. So I can able to just divide that particular window into the two parts. Then next one, that is forest. Okay, so forest means what? It is a disjoint union of the tree. Okay, so forest, whatever our previous example, suppose we just consider this particular example. Okay, so this is the particular tree. So from this particular tree, suppose I want to just design the forest. So forest is nothing but it is a set of disjoint trees that are obtained by deleting the root and the edges connecting to that particular root node. Okay, so whenever I just delete this particular node along with this particular edges, then whatever the contents or whatever the sub trees which are formed, which is nothing but the forest. Okay, so this is the particular first tree, first forest, this is the second forest, this is the third forest. So three forests are there inside the particular tree. So this is called as forest. Then binary tree. So binary tree terminology having the same terminology, but with addition of sibling. So sibling means what? Suppose सो आपण घरामध्ये असते आपल्या भाऊ किंवा बहीण. So this is called as sibling. Okay. So suppose this is the particular node. So I want to just find the sibling node, that is the node at same level, which is nothing but the sibling. So this is called as sibling. So one don't have any sibling, two have sibling, that is 3, 4 having the sibling as 5, 8 and 7. Okay, then 8 having the sibling as 9, 10, 11, 12. So these are the particular siblings. Okay. Then we have seen the particular tree. So binary tree is a data structure which is defined as a collection of element called nodes. And in binary tree, topmost element is called as root node. And each node has 0, 1 or at most 2 children. Okay, so this is the particular property related to the binary tree. So this is the most important property related to the binary tree. That is, each node has 0, 1 or at most 2 children inside the binary tree. Okay, so if the node having 0 children, it is called as leaf node or terminal node. Okay, so whatever we just discussed previously, same thing which just write inside the this particular program. Okay, so inside the binary tree, node having 0, 1 or 2 child. Okay, that's why it is called as binary tree. So at most 2 children are there. It may be 1, it may be 0. So this is the basic feature related to the binary tree. Then, so here you might observe that here root element is there. It is having 2 children. Again, this particular element having two children. This 2 having two children, but this 5 don't have any particular children. Again, 3 having two children, 6 having two children, but 7 having only one children. Okay. So this is having one children, this is having two children, this is having 0 children, this is having two children. Again 0, 0, 0, 0, 0, then 2, 2, 2. Okay. So these are the particular childs of the node. So number of childs of the node. Okay, so whatever we just given in the point, these are the children. So binary tree, the feature of binary tree is that it have either 0 children or 1 children or 2 children, not more than that. So this is called as binary tree. Then leaf node means the node which don't have the particular children. So this is the leaf node, or this one. Then similar binary tree means what? The tree T and T dash are similar if both tree having the same structure. So this particular node's name is different, but structure remains same. So that's why it is called as similar binary tree. Copies means what? Same node, same structure. Okay, so this is called as copy. So similar binary tree and copies. So say A, B, C, D, E, A, B, C, D, E. Then edges means what? It is a connecting to the node and its successor. Okay, so this is called as edge. Then path means what? It is a sequence of consecutive nodes from the root node. So whatever the node to the root node, it is a path. Path of E. Then depth means what? Depth of the node is given as the length of the path from the root node. Okay. So for example, suppose I just take depth of E is equal to, so it will just start with 0, then 1 and 2. So it is a 2. Okay, so depth of the tree of root node is 0. And height is whatever the total number of the path from the root node to the deepest tree. Okay, so height is, height of D is 1, 2, 3. Okay. So in this way, these are the particular concepts related to the binary tree. Then we have just seen the in degree and out degree, that is the number of nodes which are coming and which are going outside. Then complete binary tree means what? The tree which satisfies the two properties. Okay, so first, that is complete binary tree, every level except possibly last is completely filled. Okay, so completely filled means what? Must have two child and all nodes appear as far left as possible. Okay, so the second property is all nodes that are appeared as far left as possible. So completely means, so complete binary tree means what? It have at each level two child and mostly elements of node at left side as possible. So this is called as complete binary tree. Okay. So complete binary tree means what? At each level there is a two children and mostly the elements are left side. Okay. So you might observe this particular. So one having the two children, two having the two childrens, four having two, five having two, six having two, then three having two, and whatever the leaf nodes having the zero children. Okay, so there is no other option of one children inside the complete binary tree. That's why it is called as complete binary tree. And whatever the contents which are mostly at the left side. Okay, so all the contents which are putting at the left side, not at the right side. So this is called as complete binary tree. Okay, then next one, that is extended binary tree. So extended binary tree is the binary tree where each node in the tree either no child or exactly two child. Okay, so extended tree also, or it is also called as two tree, if node in the tree has either no children, that is same as our complete tree, or exactly two children. So only first criteria is satisfied. Inside the complete binary tree, we have the another criteria, that is most elements at the left side. But inside the extended criteria binary tree, only one criteria is required, that is the node having either zero child or mostly two childs. So inside that extended binary tree, we have the nodes having two children are called as internal node, and which are represented by the circles. Okay, so internal nodes. So this is called as internal node. Internal node. And the node having no children are called as external node, and which are represented by the squares. Okay, so these are called as external node. Okay, so internal node, external node, and the root node. So it is having two children, it is having two, then two, and two. Okay, so in this way, we can just have the extended binary tree. That is a tree which have either no child or exactly two child, and these are represented by the separate symbol. So internal nodes which are represented by the circles, and external nodes which are represented by the squares. Okay. Then next one, that is how to represent the binary tree in the memory. Okay, so to represent the binary tree in the memory, we can either we use the linked list representation or by using the sequential representation. Okay, so these are the two representations which are used to represent the binary tree in the programming. Okay, so first one, that is linked list representation. So linked list representation, here we can just having the structure. So this is the structure in which we have to just having the node. So this is our left, this is right, and this is the data. Okay, so left node address or pointer, right node address or pointer. Okay, so whenever I want to just represent the linked list representation of the binary tree, then I am having this particular node. Okay, so left part is represented by the node, then right part is represented by the right address node, and data is represented by the in between that particular left and right. Okay, so here this is the particular representation. So each node having the left, so it just having the left, right, again left, right, left, right, then left, right. So here there is no left, right, that's why the cross is given. So here cross are given because no left or right. So similarly, here no right, left, no left. Then here again cross are given. Since it is a leaf node. Leaf node. And this is the root. Okay. So inside that again, I have to just write left, right, and right. Okay. So this is the linked list representation related to the particular binary tree. Okay. So again, suppose I am having this particular case. So this is the binary tree. And suppose I want to just represent it into the linked list. Then we just having this particular chart. So each and every address is having left, data, and right. So now randomly the particular numbers are just stored, and now we have to just connect the different addresses by just taking the or just connecting the particular node. So initially one is connected to the 2 and 3. Okay. So our route is, for example, our route is started at third location. Okay. So this is the one. So I just take another. Yes. So this is the one. So one having the fifth number, that is second element at the fifth location, and the right element, that is third element at the eighth location. So we have the eighth location. So we are just pointing to the second and third at the particular location. So left is having second, right is having third. So that's why we just enter the address of this 5 and 8 inside the left and right part. Similarly, second having 9 and 14. So 9 is so left part is our 4 and right part is 5. So 4 is stored at the 9th location. 5 is stored at the 14th location. So this is our 4 and 5. Okay. But you might observe that this 5 don't have any particular children. That's why we just enter as -1. Okay. So whenever no children, okay, so -1 represents no pointing for leaf node. Okay, so in this way, these are the particular numbers which are already stored. So our task is just to calculate the pointers to that particular numbers. Okay, so this is the simple representation related to the particular. Okay, so here this is the location for the left node, and this is the location for the right node of 1. Okay, so whatever the location of this second and third, that can be just given at the 5 and 8. So these are the particular pointing to the 5 and 8. So similarly, you can just find the different locations and you can represent the different locations within the our data. So this is called as linked list representation for the said nodes. So one more example is given. So again, Amar having the two children, that is Janak and Raj. Okay, so our route is started at the third level. So Amar. So at the 9th location, we are having the entry of Janak. So let's see. At the 9th location, Janak is there. Okay. At the 13th location, we are having the Raj entry. So Raj. Okay. So similarly, the particular nodes are connected inside this particular examples also. Okay. So in this way, we can just have the particular nodes. And these are the particular empty nodes. Okay, so these are the empty nodes, empty locations available. Okay, so which are the particular locations which are not filled, which is called as empty locations. Okay, so in this way, we can able to represent the particular binary tree in the linked list format. And next one, that is sequential format. Okay, so sequential format means what? The sequential representation of the tree is done using the single or one dimensional array. Okay, so this is the particular simplest memory representation where a lot of space is required. So one dimensional array called tree is used to store the particular elements. So root of the tree is stored at the first location. Then children are stored in the location k, stored at the location 2 into k and 2 into k plus 1. Okay. So this is the particular formula which is used. So 20. So this is the root element. So it is just stored at the first location. Then second, we just use the 2k. So k means whatever the location. Okay. So second location. So whatever the second, this is the left node and this is the right node. So initially the value of k is 0. So we just use the value of k is 1. Okay. So it is just use the location. So second and third location for the 15 and 25, 35. Then fourth, fifth, sixth, 7 for these particular locations. And at the next level, 12 don't have any particular children. Okay, so that's why these two locations are empty. Okay, so why it is empty? Because I clearly write this. So this one, but this 12 don't have any particular. So that's why 12 don't have any child. So empty. Okay, so similar cases happen with the 21. So again for 21. Okay, so that's why these two locations are free. Again, we just have the 36 and 45. So in this way, sequentially, the particular data is stored. So empty locations are the locations where they don't have any particular children. That's why these are the empty locations. Then binary search tree. Okay, so next one, that is binary search tree. So binary search tree means what? It is a one more variations related to the binary tree. Variant of the binary tree in which the nodes are arranged in an order. Okay, so we have the separate chapter related to this. So we just discuss in that particular chapter what is the particular binary search tree. Okay, then expression tree, that is fifth type of the binary tree, is the expression tree, which is basically used for algebraic expressions. So to represent the algebraic expressions or operations, we just use this particular expression tree. So suppose I want to just represent the operation like A minus B, C into D, and whatever the plus sign. So A minus B, so this is the minus sign, then C into D, and this is again plus sign. Okay, so in this way, we can just represent the particular tree. Again, we can consider the second example, that is A plus B, C into D. So A plus B, C into D. So in between there is a minus sign. So we just put the minus sign over here. Again, E into E raised to F, then G minus D. So here raised to and minus, which are differentiated by slash, and all this particular differentiated by the modulus. So we just have the particular expression tree. So in this way, we can just use the expression tree to represent the mathematical equations related to that particular. Okay. So next part. So there are a few more examples that are given over here related to the expression tree. Then next one, that is tournament tree. So this is the last type.
Sir,
Yes.
वरच्या एक्झाम्पल मध्ये ई रेस टू एफ, तिथे खाली एफ आणि जी लिहिले.
कुठं?
3.2 एक्झाम्पल.
हा
क्वेश्चन
इथं
मध्ये ई रेस.
ओके 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 ओके. इथं त्यांची प्रिंटिंग मिस्टेक आहे ती. Okay, so instead of this, we are having E and F, and instead of this, G and H. Okay, so this is the particular. So it is a book printing mistake. It is not in the algorithm.
Okay.
Then आता इथे एक एक्झाम्पल दिले. ओके, आता ह्या एक्झाम्पल मध्ये ब्रॅकेट्स दिले नाहीत. So this particular example don't have any particular brackets. So in that particular case, we have to just refer the precedent chart. Okay, so precedent chart means what? The multiplication and division having the more weightage than the plus and minus sign. So that particular concept we just use while designing the particular tree. Okay, so we just start with the a plus b. So here plus operations are there, but within that particular, here inside this, the most basic operation or most preceding operation is b upon c. Okay, so we just write this particular b upon c. Then after that we are having the multiplication precedent, so we just write the multiplication, and at the end we are having minus, so we are having the minus. Okay, so whenever the precedence is not given, it will be just converted into the precedence and it will just look like this. Okay, so such things we can able to do inside this particular precedent tree. The next one, that is trigonometry. So trigonometry is the tree where the number where the nodes are treated like a player, and we can able to declare the winner of the particular player as a root node. So this is called as winner. Okay, so from A and B there is a winner as A. Again from C and D winner is D. Again from A and D winner is A. Again from D and F winner is E. E and F winner is E. From G and H winner is G. Again from E and G winner is E, and from A and E winner is A. So whatever the root node is nothing but the winner. Okay, so this is called as trigonometry, where at each level there is a one particular winner, and we can able to just record that. So whatever the concept we just seen inside the last lecture, same winner tree and loser tree. So same way we can just use inside the trigonometry. Then this is the most used concept, that is creating the binary tree from the general tree. Okay, so I just copy this particular and I will just tell the particular example over here. Creating binary tree from general tree. Okay, so here we want to just convert the general tree into the binary tree. So what are the requirements? So it is having the 3 rules inside that, and these are the particular 3 rules which are used for creating the okay. So these are the particular rules which we want to follow. Okay, so first one is that root element of the binary tree is equal to root element of the general tree. Then second is left child of the node is the leftmost child of the node in the general tree. Okay. So left child आपण binary tree चा कसा decide करायचा? तर whatever the leftmost child of the general tree is treated as a left child. Okay. Then whatever the right child of a node in the binary tree is equal to right sibling of the general tree. Okay, so this is the term sibling. That is, we have to just search the particular similar level node as a right child of that particular binary node. So these are the three rules related to the root, left, and right. Okay, so here let's see one example, then only you can able to understand. Okay, so now my intention is to create the binary tree. Okay, so this is the general tree. This is the general tree. And I want to just create binary tree. Okay. So just give me 1 minute. Okay, so here, am I audible now?
Yes, sir.
Okay. So here, now we need to create the binary tree from this particular general tree. So what is my first condition? Root of the general tree is the root of the binary tree. So my root is A. So I just draw this particular A over here. Okay, so I need to just draw here. Okay. So this is the root. Now what is my next condition? Left child of the node is the leftmost child of the node. Okay, so leftmost child is B. So I just select the B. So same step that is given inside the book. Okay, so step 1, step 2 is finished. Now, what is my third condition? Right child of the node of the binary tree is the right sibling of the node in the general tree. So right sibling of this B okay, so right sibling is not available because inside this particular program there is no right sibling. So here only left side is available. Okay, so this is the particular second stage because right sibling is not available for the root node. Then we can just go inside the B. Okay, so now our focus is moving from A to B. So here B, we just consider the leftmost is whatever the left as E, and whatever the right sibling which is available, that is C. So I just write C over here. Okay, so I just process this particular A, process this particular B, then E, C. So I'm just coming with this particular stage, that is step 3. Then most next step, that is we have to find related to the C. Okay, so since E don't have any particular children, so we can just go to the particular C. So for C, we are again selecting with the leftmost element, that is F. So we just write F. Then inside the C, there is a right sibling, that is D. So here D is included as a right child. Okay. Then again, we can have, so this F don't have any particular children. Okay. So inside the F, it is a right sibling. So right sibling is available for the F. Okay. So we are not considering that. For again, okay. So whatever the right, we can go to that particular right. That is, we just consider this particular node as a whatever the node. Then we can move towards the D. Okay, so for D, leftmost element is I. So I just write I. And whatever the right sibling for this particular D is not available, so we just stick up with this particular D. Then we can go towards the next element, that is for I. Okay, so I having the no left sibling, but we are having no left node, but we are having the right children. Okay, so here J is available. So here I just write J. Okay, so J is given. Okay, so A, B, C, A, B, E, C, F, D, I, J. So we are at the this particular location, that is up to 6th step. Then what is my 7th step? Now process J, left children is K. So I want to just process the J. Okay, so now left child is K. So I just write this particular K over here. Okay. So this particular chart, so from A, I will just draw the particular sequence of the processing. So from A, it will just come to the B, process next. Then from B to it will just come to the C. From C, it will just go to the D. From D, it will just go to the I. Then from I, it will just process the D, process the J, and from J, it will just process the K. Okay, so this is the particular sequence based on the right sibling. Now, process all unprocessed nodes in the same fashion so that the particular graph is shown. Okay. So which are the nodes which are unavailable? Okay, so which node is remaining now? We are just processing this much. Now we are just going to the step 7. Now here inside the step 7, this G and H is available now, and which is unprocessed. Okay, so E is processed, then F is processed, then all other steps are processed, but here G and H is not processed. Okay, so now the special conditions we have to just deal, that is this particular G and F at the right side of this particular F node. So here we have to just consider at the right side, that is here G, and at the right side of this particular G, again we have to consider the H. So again H. So in this way, this is the binary conversion, binary tree. After C, there is F and D. After D, there is a I and J. After J, there is a K. So D, I, one more. Just mute yourself.
I will come at the left. J will come at the left of I.
Yes,
Right.
yes. So after I, it will just take on to the J and J to the K. Okay. 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 And here we have to process the unprocessed nodes. So it is at the right of G and it is also at the right of H. So this is the particular binary equivalent related to the whole. So this is how we can able to convert the particular numbers in this particular fashion. Okay, so we have to just first stick up with the right node, and whenever right node is found, we have to just process that, go further, process that, go further, and at the end we have to process the whatever the remaining unprocessed nodes. Okay, so this is the particular example that is given, which can just convert the binary tree, general tree to the binary tree. Okay, so you might have the particular concepts which are available. Then let's see the next step. That is traversing. So inside the pre-order traversing, so traversing means what? Traversing of the binary process is the process of visiting each node in a tree exactly once. Okay, so traverser is nothing but visiting each node exactly once. Okay, so there are the three types of the traversal: pre-order, then in order, and post order. Okay, so pre-order means what? Root is processed first. Okay, so root, so root is processed first, then left node, and then right node. Then here left node, root is processed in between the left and right. And here post order means what? Root is processed at the end. So first left, then right, and then root. Okay, so these are the particular three types related to the tree traversal. Okay, so let's see one by one. So inside the pre-order, first we have to just visit the root node, then second left subtree and right subtree. Okay, so this is the sequence, that is first, second, and third. So root is processed first, then we have to visit the second, that is left, and third as a right. So let's see the example. Okay, so this is the particular example. So let's copy this particular example. And we can also copy the traversal. and we just copy one more, that is post order. And one more is there, that is level traversing. Okay, so let's see the example. Okay, so here this is the particular binary tree. Okay, so now we have just used the pre-order. So this is the pre-order, this is the in order, and this is the post order. Okay, so inside the pre-order, what happened? Root, then left, and then right. Here, left, root, and right. And here, left, right, and at the end, root. So whatever, depending on the number of whatever the position of the root, the name is given. That is pre means first root, in means in middle root, and post means at the end root. Okay, so this is my example. Now inside the pre-order, what I required, root, left, and right. So I just process the first root A. So I just write A. The left side of that particular A is B. So I just process the B. Again, B having the particular right, okay, left and right node. Okay, so we have to process the left node first. Okay, so here we just write A, then B, then D. That is left node of that particular. So I just write D. Then after that, the left of G, left of D is G. So I just write G. And after that, I have to write the right node. So H and L. So H and L. And after that, right node of B. So E. Again, whatever the right node of C. Then F, I, J, and K. Okay, so F, I, J, and K. So in this way, it will just first root node, then left. So inside the left, if again left elements are there, you have to process that particular left node and then go to the right nodes. Okay, so similarly for this particular tree, this particular same matrix is generated. So A first, then B, D, then C, E, F, G, H, and I. Then in order means what? First, we have to just start with the leftmost node. So leftmost node is G. So we just start with the G, then root node D, H, then B, E, then A, then C, so G, D, H, L, B, then E, A. So root is coming at the top. Then C. Then after C, we are having the leftmost node, that is I. So I is coming. Then after that F, that is center. Then K and J. So sequence is just same. That is root is processed at the in between. So first left, then right. So similarly for this particular tree, and in post order, first left, then right, and at the end root. Okay, so root is processed at the end. So left elements are G, then we are having L, that is right, then H, T, then E, B. Okay, so this is the left part. Then we are having the left is I, K, J, F, C, and then A. Okay, so these are the particular process. So you can just have the particular sequence. So here root is processed first. Here root is processed at the middle, and here root is processed at the end. Okay, so this is the this first traversal for A, this second traversal for B, A, B, this A, B. So these are the particular traversal methods which are included for each and every traversal inside the binary tree. And one more, that is level traversal. So inside the level traversal, what happened? We have to just process the particular tree level wise. So for A, it is A, B, C, then D, E, F, then G, H, I, J, and L, A. That is level wise, we have to just process it. And for B, we can write A, B, C, D, E, F, G, H, and I. Okay, so level wise, we have to just process. So first level, then second level, then third level, fourth level, fifth level, and sixth. So these are the particular 4 types related to the particular traversal. Okay, so tree traversal having this particular 4 types, and 4 examples are there. The next one, so all examples we have just taken. Then here one more concept, that is constructing a binary tree from the traversal result. Okay. So suppose I'm just giving the in order traversal or pre-order or post order. Okay. So in that, what is my requirement? I can able to construct the binary tree if we have given at least 2 traversal. So 2 traversal must be given. And out of that, one is in order and another is pre or post order. Then only I can able to construct the binary tree. Okay, so first traversal is in order and second can be either pre-order or post order. Okay, so here in order is given and pre-order is given. So based on that, I want to just draw this particular tree. Okay, so in order, we have to just find the root element. Or inside the pre-order also, we can able to find the root element. Okay, so root is just calculated. Then element to the left of the root, we can just take from the in order. Okay, so from in order, we have to just recognize that these are the particular elements at the left. So So these are the particular elements at the left, and these are the particular elements at the right. So these are the particular two elements that I have just taken. And again, inside the DBE, we have to just find which element at the middle. Okay, so here again in the left, we are having the B as a root, C as a particular element, and these are the two children's. So whatever the children, so all this particular is located over here. So these are the particular nodes which we want to just find. And here we just convert the whole binary tree. So this is the binary tree from this particular traversal. So traversal is given, and we have to just consider construct the binary tree. So this is also applicable inside the particular tree. So either in order or pre-order or post-order, traversal is given, we can able to construct the binary tree. So these are the particular steps for constructing the binary tree. So here again, another example, that is in order is given and post order is given. So here root is this one and this one. So we just recognize the root, and from this, whatever the nodes. So here we have to just recognize which are the nodes. So from CJ's FJ, CJ, we just want to find this particular left and right node. So here C is the root node, so we just recognize this particular as a whatever the internal node, and it is having these particular two childrens. So these are the two childrens we have to just recognize. So FJ, so something is just wrong. Here it is not I. So I is basically at the left side. So here it must be I. Okay, so here inside this particular example, I is there, and here it is okay. So here it is J. So some mistakes are there in this particular exam, but you can correct it and solve it. Okay, so in this way, this is the last corrected tree. Okay, so this is the F and this is the J. So while designing or typing the particular content, the mistakes may happen. We are human, so there may be a mistake. So in this way, we can correct it. Okay, so F, J, C, J. So J we just recognize. So F and J, and here J is at the right side. So here we constructed. Then inside the D, B, H, E, I, we just consider as a B from this particular B. So these are the particular content, and these are the post order, that is root is at the end. So here we just recognize B, and from this again we can recognize as a, these are the particular content at the this particular. So D is the left and HEI is at the right, and again we just constructed this particular string. Okay, so there are the few mistakes we just found. So 2 times we just found the mistakes inside the particular example. So these are related to the binary tree. So these are the applications where we can use the tree. So tree can be just used to store the complex data. Okay, so this is the first application. Then we can often implement the data structures like hash tables, sets, and maps with the help of tree. Again, we can just create the self-balancing tree or red-black tree, which is in our syllabus in next 2 chapters. Again, we can just store the tree structures on the disk by using this particular tree. Again, it can be just act as a secondary indices in the databases, or you can just use the important data structures for compiler construction. So different compilers that can be just created with the help of again tree. For database design or for file system directories, we just use this particular trees. So these are the particular applications related to the trees. Okay, so this is how we can able to just deal with the different concepts related to the tree inside this particular chapter. So this whole chapter is a base related to the concepts which are used inside the